Hello guys, welcome back to my channel. Today I'm going to explain solutions of the first three problems in weekly contest 190 in Leetcode. So in the first problem, what we're asked to do is that we're given a string called sentence, and another word called search word, and we need to find the first word in the given sentence that contains the given word as a prefix. So in the example, which is I love eating burger, and the search word equals to berg. So the first word in the sentence I love eating burger, where such that it contains berg as prefix, is burger, and it's the fourth word. And if there isn't such a word, we just output -1. So our basic approach is to just traverse the string and just check if the current character we're currently at is a space or not, because we need to observe that if the current character is a space, then that means in the next move we're going to move to another word, a new word, because every word is separated by space. So we can just declare another string that stores called s, that stores the current characters until we move to a new word, traverse a given string, and then check if the current character is a space. Then if it isn't, then insert our current character into the string. Otherwise, we need to empty the string and increase the number of words, because if we say space, then that means we're going to move to a new word. So we just empty the string that stores the characters and just increase the number of words. And then just check if the string we've declared equals to the given word, the search word. So that means we have found an index and a word that contains the given word as a prefix. Because, as an example, I love eating burger, we just traverse it, we have I, then we have a space. So we just empty the string, then we insert L, O, V, E, then we again empty the string, then we insert E, A, T, I, and G, and then we empty the string, and then we insert B, U, R, G. And here we have berg, so we just check if berg equals berg, which is true. So we have found an index. So we just update our answer to the index of the word and just print it. And then just check if answer exists. So if it exists, we output that, or otherwise -1. So yeah, basically that's it. In the second problem, we're given another string s and an integer k, and we need to find the maximum number of vowel letters in any substring of s with length k. So as in the first example, where it is s equals abc, iii, d, e, f, and k equals 3. So if we take every substring of length 3, we see that the maximum vowel letters are in the substring iii, which is 3. So we can solve that by using sliding window technique. So we can just traverse the first k characters of a string. In this example, k equals 3, so we just traverse the first 3 characters of a string, and then find how many of these letters are vowel, and keep that to a variable called here ans, and then traverse the other string and just check if the current character we're at is a vowel, then increase our answer. And because each window is equal to the previous window plus the current letter minus the first letter, so for example the first window of line 3 is ABC, the second window is BCI, the second substring, I mean by window. So BCI is formed by including I from the previous window, which is ABC, and excluding A. So we can just check if by including the ith character here in the second loop, if it's a vowel, so we can just increase our answer, and by excluding the first character of the previous window, we can just check if the first character of the previous window was a vowel. Then we just decrease our answer because we have eliminated that one, the first character, and then just take the maximum of this all. So yeah, that works, and it's in linear time by using sliding window. That's it for the second problem. Now let's go to the third problem. So in the third problem, we're given a binary tree, and with not values from digits from 1 to 9, and we need to find the number of paths that are from the root to a leaf that are pseudo-palindromic, and the path is said to be pseudo-palindromic if we can rearrange the values in the nodes such that they're palindrome. For example, in the given binary tree here in the first example, the number of paths from root to leaf are 2, which is the underline 2, 3, 3 and 2, 1, 1, because we can rearrange 2, 1, 1 to 1 to 1, and it will be a palindrome 1 to 1, and we can rearrange 2, 3, 3 to palindrome 3 to 3, and it is also a palindrome. So we have 2. And in the second example, we're going to do the same, and the answer equals 1. So let's just see an approach. So we can just do DFS, depth first search, and we need to observe that a sequence is palindrome if there is only at most one integer that has odd frequency. So for example, in the path 233, 233 is a palindrome if we rearrange it to 3 to 3, because the only number with odd frequency is 2. So there is one number with odd frequency. But for example, say path 231 isn't a palindrome even by rearranging it, because there are 3 digits that have odd frequency 2, 3, and 1. So that isn't a palindrome. So we just do DFS from the root and just check if the current node has a left child. So we can just DFS to the left child, then check if it has a right child, then we can just DFS to the right child, and then just check if it's a leaf node. So that means it doesn't have either a left child or neither a right child, and then just traverse all the digits from 0 up to 9, and then just check how many of these we have made that have odd frequencies, how many of these nodes have odd frequencies until now, and just check if these nodes, the number of nodes that have odd frequencies in this path, are smaller than or equal to 1. So that means we can form a palindrome by rearranging the numbers in this path. Then we can just increase our answer, and then we should decrease the frequency of the current digit, the value of the current node. So for an example, the first example, let's just visualize it. We just traverse, we have the root, and we just start traversing the tree with the DFS from the root, and we go to check actually if it has a left child or a right child. It has both, so we go to the left child, then we just do the DFS from here and just check if it has a left child or right child. It again has both, so we go to left child, which is a leaf node, and just check if the path until here 233 is a palindrome by checking if the number of odd the count of odd frequencies are smaller than or equal to 1, so there are either 0 or 1, and just increase your answer. Then go to the right child of the node 3 here in second level, which is 1, which is also a leaf node, but the path here is 231, which 231 isn't a palindrome even by rearranging it. And yes, we do that for the right subtree. So we got the right child, which is 1, then we go to the right child by doing the depth first search, and which is a leaf node, then we check the path, which is 211. 211 isn't a palindrome even by actually 211 is a palindrome, so we just increase our answer. So yeah, it's actually we just do DFS, and so the key here is to observe that a sequence can be a palindrome even by rearranging it if the count of numbers that have odd frequencies are either 0 or 1. So okay, that's all. I've explained all 3 problems. Thank you very much. Hope you enjoyed the video. See you in the next video.